Hello, I'm going to showcase IntuitionRF, which is a plugin for Blender that I wrote. It is meant to make using OpenEMS easier, especially the meshing part, and to let you use OpenEMS all from within Blender. So you can download this plugin from the GitHub page. It does not ship with a OpenEMS distribution, so you will need to install OpenEMS from the website, and you will need to have OpenEMS compiled with Python interface enabled and built against the same Python version as your Blender version is using. So in my case, it's Python 3.11. Once you have OpenEMS installed, you can install the plugin like a regular plugin and configure it to use your OpenEMS install. You can find the install instructions on the GitHub page. So I am going to show you how this works using the examples from OpenEMS and then some examples of my own. We are going to start with the simple patch antenna example, and then we will do another antenna, and then we will attempt to get a mesh from KiCad, a PCB mesh, and simulate its behavior in OpenEMS using IntuitionRF. Okay, so let's begin. I'm going to start Blender. I'm going to start it with the command line output visible so that we can see what's going on in OpenEMS. So when you start Blender and you have IntuitionRF installed like this, you will see new panels in the properties under the scene category and the object category. So here and here. So I'm going to start modeling the same antenna as in the example. So it's a 2.4 gigahertz patch antenna. It's 32 millimeters wide, 40 millimeters long for the patch, and then it's on a 60 by 60 millimeter substrate. So let's do this. I'm going to start by setting up the simulation scale. So I'm going to use a scale of 1000, so 0.001, which means that 1 meter in Blender is going to be 1 millimeter in the OpenEMS simulation. Okay, so let's make first the ground plane. It's a 60 by 60 millimeter ground plane. So let's do this. Okay, so that's our ground plane. I'm going to rename it ground. I'm going to duplicate this, make the substrate. The substrate is 1.524 millimeters high, so let's do this. Yeah, that's correct. So that's my substrate. I'm going to save it. Let's call it patch 2.4, like this. Okay. And now duplicate this. That's the patch. And it is 32 millimeters, so 16. Oh, sorry. By 40 millimeters, so 20 like this. And then 20 in this direction. So that's our patch on the top. And now we have a port that is a lumped port. It's at X position -6. So let's do this. I'm going to duplicate this, rename it. And now we have a single point. We put it at -6 on the x-axis, extrude vertically and go to the ground like this. Okay, so that's our model complete. Now we need to define the simulation and especially the simulation meshing. To do this, what we can do is go in under the IntuitionRF tab and add a default meshing line set. And this will define our simulation domain and meshing lines. So let's do this. It will be very small by default. You see it created a new object. We can scale this up to match the antenna. Let's do this. You will want to leave some space around the antenna, not have the boundaries of the simulation too close. And then we need to apply the scale and all transforms actually, and we want that for every object. So we want a scale of 1 and no translation and no rotation. Okay. Now that we have done this, what we can do is preview the meshing lines. We want to set a much more coarse smoothing resolution. So let's start with something like 8 maybe. And now we can preview the meshing lines. And you see it complains because there is no objects in the simulation. So let's fix that. What we are going to do is take everything we want in our simulation. So that's the port, the patch, the ground, and the substrate. Make it a new collection. Let's call it RF. And now we can set the IntuitionRF objects to RF like this. And this should now work. Let's preview the meshing lines. Okay. So now you see we have a default meshing lines. It does not match our geometry. We want meshing lines on the edges of our simulation. So one line like here, one other here. So we will need to add meshing lines to the simulation. There is two ways we can do this in IntuitionRF. The first way is we can select the vertices and click add mesh line X, Y, and Z here. And if I do this and preview again, you see the meshing has changed. And what happens is it adds vertices into this lines object. So you see we have new vertices here. And if we subdivide this and add new vertices, we get new meshing lines. Sometimes we get this kind of artifacts. It usually means that vertices are overlapping or that you have some weird scaling happening. So let's fix this. Okay. This, however, is not the best option for our case because when we decide to change the geometry of the antenna, the meshing lines won't move with it. So what we can do instead is remove the vertices we added like this. You see meshing lines is back to normal, and now what we can do is create vertex groups on the objects and assign anchors for IntuitionRF to use as meshing lines. So let's do this. We create a new vertex group, call it IntuitionRF anchors like this, and assign vertices to it. Okay. Now we can preview the lines again and nothing is happening, and the reason for that is that our object here is not yet a OpenEMS object. So let's fix that. Go into IntuitionRF and make this a metal plane. So AA faces, we'll get back to this later. Okay, and now if we mesh the scene again, you see something happened. We can remove the smoothing to see what's going on. And now we see that we have meshing lines that go and follow our vertices. So let's do this for all relevant vertices in the scene. So we have those two for the ground plane. We're going to do the same on the patch. Like this. Okay, and we need to do it for the port as well. And it's not happy because we have a wrong direction on the port like this. Let's make it active as well. Okay, and now we have meshing lines for every aspect of the simulation. So we can smooth it. Okay, so that's a nice meshing. What we can do now is set up the materials in the scene. So for every object in the RF collection, we want to do this. So let's start with the ground patch. So you have those options for the object type. We will use metal axis aligned faces. You have two options here. If you have a zero width object, you want to use axis aligned faces, and if you have a volume that you want to be meshed as a metallic object, you want to use volume. So we are going to use metal AA faces both for the ground and for the patch here. Okay, for the substrate we are going to set it to a material, and I believe it has a epsilon R value of 3.38 like this. And now we have the port, which is a lumped element, which is the only type supported as of now in IntuitionRF. So we want it to be a port. We have a port number. We want it to be active, which means we want to inject energy into that port. Reference impedance is 50 ohms, and it's on the Z direction, as you can see here. Okay, so now we can check that what we have done in Blender and what OpenEMS understands of the scene is the same. So we can preview the simulation in CSX CAD like this. We see that the meshing looks correct, and we have our ground plane, our substrate, our patch, and we have the port right here. Okay. So now what we can do is preview the pec dump, which means see how OpenEMS is meshing our electrical conductors, so that's the metal plates, and the port, to see that everything is going on. This is the most important part to get the simulation right. So we can click on View Pec Dump here, and we get a new object that shows us how the geometry of the scene is meshed for simulation. So here we can see that it seems to be correct. We have the ground plane that is matched, and we have the patch that is also meshed into the simulation. So that's good. Okay. So now what we can do is run the simulation. I will change the directory for the simulation so that we save the data. So I'm going to call this sim data like this. Okay, view pec dump again. And now if we show the Blender CLI output, we can see that we get the OpenEMS engine called. So that's what we want to see what's going on in OpenEMS. So now we can run the simulation. Before that, I want to change the frequency here. So we can use a Gaussian pulse or a sine wave excitation. I'm going to use a Gaussian pulse here. And because we are aiming at a 2.4 gigahertz frequency, I'll use a center frequency of 2 gigs. Like this, and a cutoff frequency of 1 gigahertz. Okay, so we should now be good to go. So let's run the simulation. So as you can see, it completed very quickly. The energy dropped to negative 57 dB in only about a second or two, 4 seconds, sorry. So that's good. It has to do with our meshing. So the meshing is quite coarse. You want the meshing to be as coarse as possible, but as fine as necessary, as is explained on the OpenEMS documentation. The legacy wiki is a very good resource as well. You want to take a look at this. Okay. So now what we can do is see how this antenna behaves. So we can select our port object, go into the object category, and then see the impedance and the S11 parameters for the port. So let's check this. And as you can see, we have a very good resonance at around 2 gigahertz, a little bit above 2100 megahertz. So that doesn't quite match what we see in the example. Sorry. As you can see, the antenna in the example resonates higher up in the, exactly at 2.4 gigahertz. The reason for that is because we lack meshing resolution, especially around the edges of the metal planes. So one way we can fix this is add the meshing lines around the metal planes. So you could go into the lines object and add some vertices all around the place, but again, they will not move if you decide to change the antenna geometry. So what we can do instead is add more anchors to the model. And because we are using a axis-aligned faces, only faces in the model will be considered in the simulation, which means that we can add lines and vertices, floating vertices, that will be ignored in the simulation, but will act as anchors for our meshing. So if we take our existing vertices, like this one, we can extrude on x-axis, subdivide, same on the y-axis, subdivide. They should be anchors as well, there you go. And now if we show the meshing again, we have a much finer resolution at the edges of the metal. So let's do this on the other side. Okay. And now let's do this here, here, here. Okay. And now we want to assign only what we want. Okay, and now we need to do the same with the patch. Let's do this. Okay, So now we have a much finer resolution on the X and Y axis around the edges of the metal. We want to do the same on the Z axis, so let's take the bottom ground plane again. Okay, extrude Z like this, add resolution here, same on the patch. Okay, and this should now add some resolution above and below the antenna, like this. And now what we want to do, as you can see, we don't have a lot of resolution inside the antenna where quite a lot is happening, so we can take the substrate and add some resolution inside the substrate. So let's go 3 cuts, 3 edge loops. Like this. Oh, sorry. Like this. And if we mesh again, like this, we have a much finer resolution inside the antenna. Okay. Check the pec dump again. This looks good. And now let's run the simulation again. So now we have more cells to simulate, so it will take a little bit longer. And now it has completed. Okay. So we can check the S11 parameters again. Let's see, and as you can see, it got way up, almost where we want it to be, so almost where it's expected, so 2377. Now we are still not quite at 2400 megahertz. There is a couple of reasons for that. It could be that our resolution is still not high enough, so we can check that. We can change a smooth resolution, make it lower, like this, and run the simulation again. Okay, let's see. So it's better, and what I didn't do, and is in the example, is set a kappa value for the substrate. So it has this kappa value, which is 0.004, I think. So let's use this and put 0.004 here, run again. Okay. It got a little bit lower actually. Let's bump the resolution again. Okay, so now we have results that very closely match the example. We have a resonant frequency of 2396 megahertz, so 4 megahertz off from the reference 2.4 gigahertz. Okay, So when you show the S11 parameters, it also figures out the resonant frequency and uses it in this parameter here. We can also show the impedance plot, which looks something like this, and you can see our reference 50 ohms impedance, which is the magnitude that you want, is around here. We don't quite reach 50 ohms, but this is definitely the resonant frequency. Okay. So now that we have done this, what we can do with that resonant frequency is compute the directivity at that frequency for this antenna. So we can click compute near field to far field. It can take a while, and it gives us a radiation pattern. It's the E field, far field view, magnitude of the E field pattern that we see here. We could see all kinds of patterns, H field, polarization, etc. But for this, we are only interested in the far field view of the E field magnitude. So we can scale this up, and this is very consistent with what you'd expect from a patch antenna. So it has a very good radiation pattern on the top, and nothing below the antenna, and very little on the sides. Okay, now if we want, we can add some coloring to this. So let's get into the shading editor, go add the HDRI like this. Okay. Okay. So now if we want some nice coloring, what we can do, because it's always centered around 0, 0, 0, so what we can do is add geometry, take the position, get its length like this. We probably need to scale it. So it's likely a very large value because we have a scale of 1000, so let's divide it by 1000 to begin with. Maybe a little bit bigger, like this. Okay, and now if we add a ramp, we can see what's going on. Okay, okay, so let's see, 0.05 maybe. Yep, that seems good. And now we can add some colors. So let's say that lower value are blue, highest value are red, and in between let's make it green. And then some scaling again. Still not quite there. 0.15. 0.2, yeah, that's it. Okay, and this gives you a nice visualization of your radiation pattern for your antenna. This, by the way, has no scale because it's a far field view, so its scale is not in any way related to the scale of the antenna, so you just want to display it in a visually pleasing way. So now what we can do all kinds of stuff. We can make it way bigger like this. Need to scale this down like this. And then maybe we can make it a volume with a density. Let's turn up this. Okay, so that gives us a nice render. We can remove the pack dump. Let's make the metal parts metallic. Okay, maybe it's actually too big. And what you can see here is some Z fighting. That's expected because we have exact coordinates match. So to fix this, we can just move this a tiny little bit down like this. The substrate is not a metal, so let's call this substrate. Make it non-metallic, quite rough. Let's say it's some kind of ceramic material. I don't know what it is, I just know that it has a epsilon R of 3.38. And the bottom is metallic as well. Okay. So this concludes our first example from OpenEMS. I am going to show you a second example. We are going to model and simulate a planar inverted F antenna. So I'm going to show you how this works. Okay, so let's make a new file like this. Again, I'm going to start by setting up the scale, so 0.001 like this. I am going to start with a 30mm long antenna. So let's do this. And let's make it 40mm wide for now. Sorry, 20mm wide. So 10. And make it 15mm high, like this. Maybe that's a little bit too high. Okay. Now we add some legs. Okay. And now we cut a slot like this. And our feed point will be here, and we will have a metallic ground plane under the antenna. So let's do this. Make this a separate object. Like this. I'm going to rename this to ground. This will be the antenna. Save this to a new project like this. Okay, I am going to chop off that leg and make it the port like this. And then I am going to add the meshing line set, just as we did before, like this. Scale it way up, apply the transformation. So that's our simulation domain. We can move this up a little bit like this and scale it up some more. Okay. Now I am going to make a new collection for the RF objects, like this. Set it here, set the resolution way up, and show some meshing. Okay, let's go with 4, like this. So that's our antenna model complete. Let's make the top antenna a metal with axis-aligned faces, same for the ground plane. And let's set the port. Okay, so that's our simulation setup. We can now preview the pack dump. Again, I'm going to change the simulation directory. Like this. Okay. I happen to know that this kind of frequencies is about right for this kind of antenna. Maybe we can bump it a little bit, let's say 1 gigahertz, and then 500 megahertz cutoff frequency. Okay, so now we can preview the simulation CSX CAD. And this seems to be correct. As you can see, when you have multiple planes, it gets discretized as one simulation object for each plane. So you have like antenna 0, 1, 2, 3, etc. That's every plane here. What we can do to reduce the amount of plane is remove what's unneeded, like this. But that's not really required. You can leave it like this and it will be fine. Okay. So now we can preview the pack dump like we did before. Let's see. Okay, so it's unhappy. And the reason for that is that we didn't define any meshing lines that would match the metal planes. So let's do this. So I will use the same method as before and add anchors. So let's select those 3 vertices like this. Assign, and now if we preview the meshing, so that's correct. Let's add some more here, here, here. Assign, preview the meshing lines. Now we need this one, and we should be good for first meshing. Maybe add this one too, like this. Okay, and add the ground plane. Like this. Okay, so our base meshing should be complete. Let's check. As you can see, it matched the antenna. Now we can add the smoothing back in. And so that's our perfect electrical conductor meshing. As you can see here, we probably lack a anchor here. Let's add it like this. Yeah, that fixed it. And this is good. So we can run the simulation now. Should be quite fast. Okay, it completed almost immediately. And now if we go into the port and see the S11 parameters, we can see that we have almost no resonance at all. It's like negative 0.01 here, so that's not good. So what we can do is see if it happens somewhere else. So increase the cutoff frequency and run again. Okay. And it does happen way higher at 1600 megahertz. Okay. Now, what we didn't do on the patch antennas, it does change the simulation results. I'm going to use the same method and add some wires that define some meshing lines. So let's do this. Okay. Okay. Let's add some resolution on the Z axis as well, like this. Going to add some around the ground plane as well. Like this. Okay. So this looks good. Let's add some resolution here. Okay. Okay. Some more here. Okay. And we probably want some resolution within that cutout here, because that's where quite a lot is happening. So let's add that. So it already has resolution around here. Here is okay too, and we want to cut here. Like this. Okay. So now we can see that we have good resolution where it's needed. Maybe we can add some more in here, like this. And this looks good. And then maybe some here and some here. And this should give us nice results. Let's see. Okay, so this looks good. Let's run the simulation again and see if it changed anything. Should take longer because we added cells. So what you see here is the energy in the system doesn't drop, so the simulation never completes. So that usually means that the energy gets stuck in the system, or that you have a meshing issue. So let's stop this. get back to the meshing. Let's preview the pack dump. It does look good. So maybe there is another issue. Let's change the cutoff frequency again. Run the simulation. Okay, so I figured out the problem. So if you get this kind of warnings here, it means usually that you have a cell in the system that is way too small, creating a very small time step. So let's fix the meshing, figure out which cell is too small, and figure out how to fix it. Okay. So usually you'll see when cells are too small because the meshing lines will be very close to each other. This does not seem to be the case here. Maybe around here we have a problem, might be. Let's make sure that we have no vertices in here. And then let's check. So sometimes if you have multiple vertices that have the same x coordinate, for example, they can overlap. So let's try to use the minimum amount of vertices for this simulation. Let's remove all of those. Show the meshing lines like this. Okay. Now we add back what we need and only what we need. So this, this, these two, let's see. Okay. These. Okay, so this looks much better now. We have lines almost everywhere we need. Maybe we can add some lines. Let's see. Those two. We probably want a line here too. Okay. Okay. Use a pack dump again. This looks good. This looks good. Now, when you see when you preview the pack dump, you can actually get the same warnings with time step size. So we don't have this warning here. So this looks good. Let's run the simulation again. Okay, so it doesn't work. So something's wrong with the meshing. Let's figure out where it's wrong. Oh, it's probably lacking a anchor here. Let's try again. And it might be lacking resolution here. Add those two like this. Okay, this looks good. Run the simulation again. And sorry, it doesn't like the meshing for some reason. And it does not have a line here, so should probably add this too. Like this. And now it's happy. Okay. And we can see that we have a reasonable number of time steps for the excitation signal length. So that's a good indication too that it's working. So as you can see, it completed very quickly. Now we had the resonant frequency at the port of 1600 megahertz. So let's see if this moved with the increased resolution around the edges. And it did change something. Now we need to bump this again, run the simulation again. Okay. So it went up. It's now at 1700 megahertz with a quite nice resonance, actually, negative 10 dB, below negative 10 dB. Now what we can do is tune this antenna for a different frequency, and because we have assigned anchors directly into the mesh, we can actually edit both of these at the same time. Grab all those vertices like this, grab all of those like this, make the antenna bigger, and now if we preview the pack dump again, as you can see, it meshed nicely. And we can, oops, what it didn't do is grab the port as well. So let's get back like this, take the port object as well. Okay. You want to make sure that you're grabbing the anchors as well, like this. View the pack dump. Okay, we probably want to leave some more room again, around the antenna. So let's scale the lines up. Like this. Preview the meshing lines again. Yeah, that's much nicer. Now we can run the simulation again. Okay. And now what we can do is see where that takes us. Okay, and now we have a antenna that resonates at a frequency of 1400 megahertz. Okay, let's see the impedance plot, and as you can see, we have the main resonance here at a 50 ohms impedance magnitude. It's actually here, a little bit above 50 ohms, it's 67 ohms. And what we also see is that we have maybe a second resonance way up in frequency that is consistent with this kind of antennas, which you can create a two-band antenna with this design. Okay. Now we can do the same as we did previously and get the far field results. So if we go back to the simulation, as you can see, it put the resonant frequency here, and if we compute the far field, we get this radiation pattern here, which is very consistent with this kind of antennas. And then again, we can add some nice rendering. Like this. Okay. And then let's apply scale for this. Like this. Okay. And then again, like this and like this. And then tune the scaling to get a nice visualization. Let's say 0.2, 0.3. Okay, this is nice. Now we can maybe drop the alpha to see inside the antenna, make it slightly bigger like this. Like this. Make this metallic. And there you have it, a nice antenna simulation. Now the third example that I want to show you is how to simulate what's going on in a PCB, like simulate coupling between PCB traces, stuff like that. So what we are going to do is first I'm going to create a new file, then I'm going to jump into KiCad, make a new project. It's called KiCad example, like this. Okay. I'm going to jump straight into the PCB editor. Never mind schematics or anything like that. We just want to be able to export a PCB. So let's make it a 54 by 54 millimeters PCB, for example. Let's add a copper pore on the sorry, like this. Okay, on both sides, like this, this. Oops. Okay, so that's our copper. We should see it on both sides. This is correct. It's a 2-layer PCB, but we could do the same with 4 layers. And now let's add some traces. I'm going to make them quite large so we can easily see what's going on. Let's go with a 0.5 millimeters trace, and let's use a 0.25 millimeters clearance. Okay. And now I'm just going to place some random traces around the PCB. Let's say something like this, and let's say that we have a trace that is going pretty close in between the two. And now what we could also do is remove some copper pore in the middle to see what's going on. So let's make a key pot area on this and like this. So it doesn't work because we need to say what. Okay, copper fields like this. Okay. And now what we have is a basic PCB, and we are going to attempt and see what's going on in here, if we have coupling or anything like that. It's not impedance matched traces, but it will be interesting to see what's going on when it's not matched with anything. Okay, so now that we have this, I am going to export this PCB. Let's export it as a WRL file. Let's put it into here, KiCad example like this. We want to use probably meter here, and okay. Jump back to Blender. Let's open the PCB. So import file, our KiCad example like this. Okay, so it's not happy with the way Blender handles smoothing in 0.41, but never mind. We still have the geometry. Let's zoom in on the geometry to see what size it's at. Let's scale it by a factor of 1000 like this. And as you can see, we are going to scale it by a factor of 1000 again, because we want a 1000 scale between the two. So we had like 1000 scaling between KiCad and Blender, and now we want 1000 scaling again for the OpenEMS simulation. Okay, so let's do this again. And now we should have a 50 by 50 meters PCB with the traces on the top. Okay, so let's save this. Okay, now we have quite a lot of geometry. For this example, I'm going to ignore the finish on top and on the bottom of the PCB, so I'm just going to remove these green layers here and just leave the substrate and the copper planes. I'm going to rename this substrate like this. I'm going to rename this copper top, this one copper bottom, like this. And now I am going to remove everything else like this. We should have 3 objects now. Okay, and they should be 50 by 50 meters. So let's apply the scale for everything. Okay, and now this should have a yeah, there you go, -65 to +72, sorry, 65 here. So that's consistent, I think, with this. It's it should be 54. Okay, so some scaling issue here. So let's import the file again and start over. Oh, that's the problem. So let's put a scale of 1 here. Okay. Zoom in on this. Scale it by 1000 like this. There is some weird scaling going on, so let's say this is a scale 1. All transforms, okay. Scale this by 1000. We should have it somewhere. Let's move it first, apply transforms, and then scale like this. So this is now still not what we want, so probably a scaling issue here. Let's use millimeters. Okay. Now we should have, so that's -10 and that's +10. So it's still not the correct scale. It's 20 meters. So let's multiply everything by 2.54 because it seems that there is a inch scaling issue. So maybe we can do the opposite and say it's 1 inch like this. Okay. And now we have a -10 to +11. Scale everything by 2.54 like this. Apply all transforms. And now it's, oh sorry. Like this, apply all transforms. Okay. And now we should have a, so that's our PCB size here. It still is not correct because we want to have it 10 times bigger. Like this. And now we have a PCB size of 54 by 54 millimeters, just as in KiCad. If we do something like this, yeah, 54 by 54 millimeters. Okay. So now we just reapply all transformers again, center it around the origin. We remove everything we are not interested in, like this. And we keep copper top, copper bottom, so substrate, and everything else we remove like this. And now we have our traces. As you can see, we have some Z fighting. That's expected because we should have. Oh, there is a small gap in here which we want to remove. So let's do this. Same on the bottom. Okay. And now we want to do the meshing for this. So let's go into IntuitionRF. Scale is going to be 0.001 again. And now we are going to add a default meshing line set and scale it way up like this. Now, because we are not interested in the far-field results in this case, we can have a simulation boundaries much closer to the PCB. Because as long as we have perfectly matched layers on the side, it should be okay, and we are not expecting to see any decent far-field results from this simulation. It's not the point. Okay, so now let's apply the scale. And now for the meshing, this is where you actually want to use vertices on the meshing domain here and not anchors in your PCB. The reason for that is that you may have vertices that are close but not exactly the same coordinates. and you don't want to have automatic anchors be very close but not overlapping each other exactly, because that will make very small cells and will lead to a very long simulation time. Let's add the meshing manually. I am going to go with a rough resolution to start with. Add some meshing lines, preview. Okay, it's not happy. Let's take the substrate and copper planes, move them to a collection like this. Okay, and now mesh again. Okay, so that's our base meshing. So now let's edit, let's hide the substrate. It will make the meshing easier. And now what we want to do, we are going to take the vertices that are on the boundaries and add them as meshing lines. So in this case, as you can see here, those vertices are close to each other on the x-axis, but are not exactly at the same position. So I do not want to add them at the x-axis because it will make meshing lines very close to each other. So what I will do is add them only on the y-axis. So let's do this. And now if we preview the meshing lines, we can see that it added those boundaries here quite nicely. So now I'm going to select only one and make it a boundary on the x-axis. So now we have this single line. We do the same on the other side. This. Make this a x boundary. We are going to do the same at those corners. In this case, we can add them on x and y. So let's do this. And now I am going to do this copper trace here. Let's do this on the y-axis. So this is correct. Let's do this and this on the x-axis. This is good. Same here on the x-axis, like this. And now let's map. Let's make the same for these two on the y-axis. So now we have some nice meshing lines for these ends here. Let's do the same with the boundaries of the copper pore. So this. Okay, so now our meshing starts to look really nice. We may want to add some resolution in between at the edges. We'll see about that later. We have no lines on the z-axis, so let's fix that. Going to add this on the z-axis. I want the copper on the bottom to also be on the z-axis. Let's see, like this. Okay, and so that's a quite good basis for our meshing. Let's see how it looks with smoothing. Now what you see here means that you have two vertices that are overlapping. So let's in the lines meshing. So let's fix this. And now if we merge by distance and mesh again, as you see, it fixed it. Okay. So let's now add some, make it finer like this. So this is already quite good. Now we can refine this even further and add some meshing around the metal edges. And we can probably add these two vertices too on the x-axis like this, so that we have some meshing in here. Okay, let's do the same here on the y-axis like this. So this looks good. I think I forgot some here. The x-axis like this. Same here. Okay. This looks good. And now let's subdivide the to add some resolution in between. Sorry, like this. Now what we can do is just take those vertices here, hit subdivide, and maybe we can add 2 cuts. And now we have some much finer meshing in between the traces and the copper edge. And we can probably add some meshing here and probably here too, like this. Now this same. This looks good too actually, so let's leave it like this. Can probably do the same here and here. Let's subdivide this. Okay. And maybe here. Okay, and now okay. Okay, and this should work. Maybe this is too tight of a meshing here. Let's remove one of those. Okay. So that meshing looks really nice. Let's see how it translates into a pec dump. So let's check this first. So as you can see, we haven't defined the objects as being IntuitionRF object, or rather OpenEMS object. So let's make the copper bottom and top AA faces, and this one too. And the substrate is going to be a material. Let's leave it with the default 4.6 epsilon r. And now if we check this, now we get this messy meshing, but it's usually it shouldn't be too much of an issue. Okay, let's preview the pec dump, and it is not happy because it cannot find anything. So let's see. Let's make this, scale it on the z-axis. Okay, so that fixed it, but not entirely. As you can see, we still are missing some faces. And the reason for that probably is because okay, so sometimes you have issues with small errors in the floating point numbers, so you just scale to 0 on the axis. That is problematic, and it should fix the issue. And we have a nice meshing on the top and no meshing on the bottom, so let's do the same on the bottom. Edit both at the same time. I'm going to X-ray mode, select the bottom, scale it to 0 on the Z-axis. And now if we preview the pec dump, there we go. We have meshing on both the top and the bottom, and as you can see, the copper traces are nicely meshed, as is the rest of the copper port. So this should give us some pretty neat results. We still have that issue where we have some overlapping vertices on the edge here, which is not what we want. Let's fix that. Okay, see the back dump again, and as you can see, scaling seems to interfere with the way okay. Okay. Okay, so now both the meshing and the pack dump look fine, which means that we can now add our input port. I am going to place it on the straight trace, and so I'm going to hide the substrate like this. I'm going to place it on this side of this trace. So what I'm going to do is take that edge, duplicate it, make it a new object, call this port. I'm going to extrude this on the Z axis, and now I am going to place my cursor on this edge like this, on this point, and scale this to 0 on the Z axis, and this should now touch the bottom and top copper plates. Okay, so let's make this a port like this. Let's say it's a 50 ohm port on the Z axis. We don't really care about the impedance here, we just want to inject some kind of power and see what's happening. Okay, those traces aren't matched in any way anyway. So, okay. Now we should be able to run the simulation. Let's get back here, show the substrate again, check the pack dump again. Okay. Now this pack dump we should already be able to visualize in ParaView. So let's open ParaView, and and the reason we don't have it here is because we want to set the output directory here to this. Let's call it sim directory. Okay. Pack dump again, jump to ParaView, and now we can open this. And so that's the pack dump from our simulation. Okay, so now let's run the simulation. Let's start with a quite low frequency, so let's say 200 megahertz with a cutoff frequency of 50 megahertz. And now if we run the simulation, so it complains about polygons not being used, but the pack dump shows us that really this isn't an issue. And it might take a very long time, because as the simulation is not acting like a antenna, the energy just bounces around the place. So at some point it will dissipate, and we can see the results, but sometimes it can stay in the system for a very long time. So now this completed, so that's good. So let's jump into ParaView, and let's now see what's going on. Oh, and I forgot, before we can do this, we actually need to add a dump box to record what's going on in the simulation. Otherwise it just deletes the data as needed. So let's do this. Let's add a cube, scale it way up like this, We want the whole cube to be inside the simulation domain. Let's do this, and let's do this. Okay. And this is going to be our E field dump box like this. And we want that to be in our RF object collection as well, and make it a dump box for the E field over time. Okay, now we need to run the simulation again. This should take longer because we are recording a great deal of data to the hard drive, so it slows everything down. Okay, and now we should be able to open the results. So that's these files here. So dump over time. It comes as a simulation box. So let's make this a surface output with the E field like this. And now if we play back, as you can see, it turned red immediately, which means that we need to adjust the color scaling. So you can click this button to do it automatically for this frame. And now we should be able to see what's going on like this. Okay. Now what we can see here is a E field magnitude at the surface of the box, but that's not exactly what we're interested in. We want to slice between the top copper plane and the ground copper plane, because that's where things are happening. So let's go Z normal, hide this, show this, and if we go into the 2D view here, we should be able to see where it's going. So we need to make the slice a little bit higher, make it, let's say, 0, negative 0.05, 1 maybe, yeah. Okay, and now we have our slice, which is between the top and the copper bottom planes. Okay, and now we can play it back again. I'm going to hide this, and now we can see what's going on between the copper traces. So let's do this, and as you can see, so here you can see what's going on in the PCB. Now this is for fairly low frequencies, so we can simulate again for higher frequencies. So let's say we are going into the gigahertz range, so let's put 2000 here and 500 here. Now we run the simulation again. Okay. Now we open the simulation again in PowerView like this. What we can do is reuse that same slice and put it on the new simulation data like this. And now we can see what's going on at a much higher frequency in the gigahertz range. And as you can see, here we can really see the waves propagating in the system. So now what you see here is that we wrap by the E field direction, and because we have a copper plane cut out on both the top and the bottom, the direction of the E field goes mostly to the other copper traces or to the top copper pore, so sideways from the traces. If we had this not cut out the bottom plane like this, we could rerun the simulation, but we'd have to redo the meshing again. Then we'd have the E field not be directed towards the sides, but really to the bottom, because it's much closer. And that's what we can see at the start of the traces. So if we get back here, as you can see, if we can increase this scale here like this, and make it points again maybe. As you can see, it goes up and down when there is copper underneath it, and then it goes sideways when there is a copper cutout. So this is maybe not the best representation. Let's get back to surface again. And then you can also see how the waves bounce around, so it's making a stationary wave all across the surface of this PCB. Okay, so I hope you found this interesting. I have released this on my GitHub page. It's very, very new and not mature. I think you should probably check out the OpenEMS project first. It was made by Thorsten Liebig, and it's a great project. There is lots of documentation, both for MATLAB, and you should probably read the legacy wiki too, and the Python documentation. And you can do quite a lot with it. There's also all kinds of tutorials for waveguides, microstrips, all kind of things. So check this out. It really is a good starting point. and it's probably best to be familiar with the way it works before you use IntuitionRF. Maybe there will be evolutions on IntuitionRF to make it a node-based simulation. So let's say that we have something like this. This could be nice, like have some kind of simulation and then have some nodes that are new dedicated geometry nodes for RF simulation. So this way you can make it a custom simulation each time and have the outputs piped to whatever you want, and maybe sweep parameters using Blender's geometry nodes, both geometry creation abilities and also maybe model a geometry the classic way and then bind it to new hook objects and move around the vertices with the hooks. So that could be an idea. Please let me know what you think if you would like that. For now, it's more similar to the classic simulation way, to the classic Blender way of doing simulations. Okay, thank you for watching. See you next time. Bye.